Hello everybody, welcome back to Fundamentals of Physical Geography. Over the course of the module we've talked about environmental change, climate change, sea level change, the way that things change over time, and we've also talked about landforms and landscapes and the processes that create them and geomorphic process environments. In this session we're combining those two things together and we're looking at how landforms and landscapes change over the course of time. Now, one fairly obvious connection that you've already made, I'm sure, is that given that landforms and landscapes are controlled by processes and processes are controlled by the nature of the environment, it makes sense that if the environment changes over time, well, then landforms and landscapes are also going to change over time. But environmental change is not the only driver of landscape change over the course of time. Environmental change is a really important part of physical geography, but it isn't the only driving force, it isn't the only controlling factor. Now, you're already familiar with some of the classic theories of landscape evolution. We've talked about W.M. Davis, for example, and his geographical cycle. We're going to revisit that today, and we're going to compare it with another theory of how landscape change can occur over the course of time. In doing so, we're going to encounter some new concepts, for example, the idea of geomorphic equilibrium, and we're going to try and embed that in our understanding of landforms and landscapes, environmental change, and the way that landforms and landscapes develop over the course of time. So just to review where we are, what we've done so far, we've talked about the environment being a driving factor behind the processes that control landforms. We've talked about the fact that environments change over the course of time. We've talked about climate change and sea level change, for example. And so it's clear that in order to understand landscape change, we do need to understand environmental history. And that's what we're going to talk about next time when we look at the Ice Age and its impact on the landscapes of the UK as a nice example of that long-term environmental change actually being a key driver in landscape change. But there are also some other ideas that we need to think about. For example, the fact that landscapes don't necessarily respond immediately to impulses for change. So, for example, there isn't necessarily an immediate response to environmental change in the landscape. And different parts of the landscape might respond at different rates. So after an initial environmental impulse for change, there might be different lengths of delay before different parts of the landscape respond to that impulse for change. That's giving us complexity in the response. Also, different processes take different amounts of time to operate, and simply the operation of any individual geomorphic process doesn't occur instantaneously, it occurs over the course of time. Different processes operate at different rates, so combining that into our idea of landscape change over time, there are lots of different things going on, responding to changes in different ways and operating at different rates. Some of those responses aren't linear. It isn't necessarily the case that a small impact leads to a small response. Sometimes a very small impulse of change can lead to a very big response, and sometimes a massive change in the driving factors can only result in a relatively small change in the outputs. Responses aren't necessarily linear, and often there are responses to those. So we make a change in the environment thinking it's going to rattle through the system, but sometimes maybe there's a negative feedback that stops that change, or sometimes there's a positive feedback that amplifies or accelerates the change. So there are lots of different things to consider when we're trying to understand how landscapes change over the course of time. It isn't necessarily as simple as you'd think at first glance. So I'm just going to give you these questions to think about to begin with. Why do landscapes change through time? Now, I imagine that some quick answers will be springing to mind straight away there, and the obvious ones would be to do with, well, climate changes over time, therefore landscapes change in response to that. Yeah, there are those kinds of answers that you can give. And to that I'll say, well, okay, so why is it then that landscapes can change through time even if the environment is stable? Even if we've never had any more climate change, never had any more sea level change, would landscapes then just stop developing? Or would they keep changing even in a stable environment? So that's something to think about. Here's another set of questions or pair of questions for you to think about. The world is very simple, discuss. I quite like that as a geography exam question. The world is very simple, discuss. Or put that the other way around, the world is very complex, discuss. Well, which of those do you like? Do you think the world is very simple? Or do you think the world is very complex? I'm not necessarily talking on a life scale here. I'm focusing on the scale of physical geography. But is physical geography, the physical geography environment, is it pretty simple or is it pretty complicated? Now I'm going to give you a third slide of questions to add to those two. So far we've got why do landscapes change even if there isn't a change in the surrounding environment. Then we have, well, is the world simple? Is the world really quite complicated? And the third question I'm going to ask you is, how long is the coastline of Britain? And that isn't a straightforward factual answer that you're going to come up with there. I'm not expecting an answer of 7,000 miles or something like that. You can look it up in Wikipedia and it probably will give you a number for the length of the coastline of Britain. I wonder whether you believe that number. What do you think is the length of the coastline of Britain? So I've given you a bunch of questions there to think about. I'm now going to suggest, I'm not going to give you a cup of tea and a biscuit, but I'm going to suggest you might want to take a break, pause the video, put me on hold for a minute, and just go back and look again at those questions, have a cup of tea, have a think about it, and have your own opinion about the answers to those questions before we move on with the rest of the video. So pause the video, come back in a couple of minutes. Okay, well I hope you had a nice cup of tea. Let's think first of all about the length of the coastline of Britain. The answer to that one, of course, is, well, the length of the coastline of Britain depends on how close you look or how precisely you measure it. If you run around the page of an atlas with a 6-inch ruler and measure the length of the coastline, it'll come out to a certain length. But if you look closer and measure in between all the nooks and crannies, the length will get longer. And if you look even closer, if you get out there in the real world and instead of measuring it off a map, you actually walk around the coastline, going in and out of all the little bays, or you get a team of students with 6-inch rulers to go out there and measure in between every rock on the coastline. It's getting longer and longer and longer the closer we look. So we hire our team of mice or ants with microscopes to go out and measure in between every sand grain, in and out. And it gets, well, the closer you look, the longer it gets. Theoretically, almost infinitely longer. If you look closely enough, would the coastline become, certainly a meaningless length, more or less an infinite length. So the closer you look, the bigger it gets. Or put that another way around, it depends how long your ruler is. If you measure it with a big ruler and measure it roughly, it will be shorter. If you measure it with a tiny ruler and measure it very precisely, it'll get longer and longer and longer the smaller your measuring stick is. So what about that the world is very simple or the world is very complex question? Well, you can feed into that now that the answer to that, well, what you see depends on how close you look and also for how long you look. We've encountered that previously in the module. We talked about time as an important concept in physical geography, and we talked about cyclic, graded and steady time, and made the point that what's important in a landscape, or what's important in geomorphology, kind of depends on the length of time that you're looking at your landscape for. Different things are happening over a very short time spell, you might not notice much change, from what's happening over a really long time spell when you're going to notice different changes and different things are going to be important. So the scale at which you look at things, whether we're talking about a time scale or a size scale, well, scale really does matter. It really alters everything. What you see depends on the scale and the time scale as well as the spatial scale over which you're looking at it. And that's true not just about the geomorphology, but about most things. And going back to your world is simple or world is complicated question, well, it kind of depends how close you look. Let's take physical geography. You look at it from pretty far back and you think, yeah, I kind of get the hang of physical geography, it makes sense. Then you come in and you look a little bit closer and you see some of these complicated theories and some of these complicated connections and some of the plural and contested aspects of the discipline. You think, well, actually, this is getting quite complicated now. But keep looking closer, and as you zoom in and look even more closely at these as you thought, complicated ideas and these complicated connections, as you look really closely at them, they kind of resolve into a pattern that starts to make sense again, and you can see how all these connections work as a system within physical geography. So it was simple, then it was complicated, then it's simple again. Look even closer, and some of those connections will get really difficult again as you get into the real detail. So as you look closer and closer and closer, I would say that you kind of switch between a nice straightforward understanding of everything to a more complicated understanding to again a more simple, and it kind of changes. But the point is, as you look from different scales, you see different things. Whether it's understanding your conceptual picture of physical geography, or looking at what's happening over different time scales in geomorphology, or trying to measure the coastline of Britain, but doing it in lots of different ways, looking closer or not so close at the coastline as you're doing it. Now this is a really interesting, well, this has really interesting implications for physical geography, because straight away now you're beginning to see, well, okay, so maybe there isn't a single answer to any particular question. There are always going to be different alternative answers depending on the time scale over which you're looking at the question, or the spatial scale from which you're looking at the question. And that's true. It isn't a bad thing. It's the nature of the discipline, it's the nature of many disciplines, and that's one of the reasons why we talk about physical geography being plural and contested, because what you see depends on how you look. You can look in lots of different ways, and then you get lots of different answers, and we're trying often to resolve, well, which of these many correct answers are the ones which apply in our particular situation. And that certainly applies to what we're talking about now, understanding geomorphology in the context of environmental change. So time is a really important issue. We've already established that earlier on in the module. So I want to come back now and remind you that we've talked previously about what you could call a time-dependent conceptual framework. W.M. Davis, in his work on landscape evolution, his geographical cycle, and he talked about the fact that processes operate through he didn't really specify about processes, he was talking about stages through time, that as time moves forward, the landscape, because of erosion, because of denudation, the landscape moves forward through these stages of time. And in Davis's conception, time almost itself became a driving factor, but certainly change through time was kind of inevitable, or was built into Davis's model. But I want to compare Davis's model with a time-independent conceptual framework, Hack's model of dynamic equilibrium. I'll take as an example, just to illustrate how you can see the landscape, you can see environmental change and landscape change in different contexts. And under Hack's model, processes and morphology, or process and form, can be in balance in such a way that even though things are still happening, the landscape remains dynamic, stuff is going on, but the overall morphology won't necessarily change through time in the way that Davis argued. Davis argued it gradually lowered and flattened to a penny plane. Well, Hack says, well, not necessarily. So let's have a look at that in a little bit more detail. So this is a reminder of Davis's model. He talked about young, mature and old, senile landscapes, and he said that at the youthful stage, after an area of land has been uplifted, it then gets worn away. And this is his model for a temperate or fluvial environment, and he says the land surface gets worn down, and initially we have these youthful V-shaped valleys. Then gradually, as the valleys flatten out and reach mature age, and we get meandering rivers and floodplains down towards the lower end of a system, in old age, we have a penny plane, almost flat penny plane. And he talks about pennyplanation as being that process of flattening out the land through time. Then we get more uplift and the whole thing starts over again. That's the cyclic model in Davis. So on the left-hand side there, you've got a version of Davis's model, and on the right-hand side there, I've got an alternative model, Hack's alternative model, which begins in the same way, if you like, and you have a youthful stage, you have this initial stage of the landscape being worn down or being altered by geomorphic processes. But then Hack says we don't necessarily have to progressively keep flattening this landscape to a penny plane. We can kind of maintain the morphology we have in that mature stage, and we might get gradual lowering, but we won't necessarily get gradual flattening. We can retain that same morphology. That's what he's saying. How on earth can that work? How can that be? Well, let's have a look at the thinking behind that. So let's think first of all about what you would expect to happen in different situations. Take these graphs one at a time. Start with the one on the left hand side. And we've got the erosion rate happening in any particular location and the gradient that we're on in a particular location. So what's going to happen at a low gradient? You're going to get lots of erosion. I mean, just imagine in common sense you've got a hillside. Would you expect to get more erosion happening on a steep hillside or more erosion happening on a gently sloping hillside? You get the rain falling in the inside on the hillside, you get the water running off or whatever. Where's the erosion going to be fastest? On the low slopes, the flatter slopes, the shallow gradients, or on the steeper slopes, the sharper gradients. And as that graph shows, common sense suggests that as you increase the gradient that you're working with, you're likely to get more and more erosion. Low erosion happening on shallow slopes and more erosion happening on steep slopes. So that's what the left-hand graph there is indicating. What about the right-hand graph? Well, here we're looking at what you'd expect to happen on rocks of different lithological resistance, or surfaces with different lithological resistance. What's that? Lithological just means to do with rocks. Resistance is, well, how easy is it to erode? So basically, if you're on a very hard rock, you'll have a high lithological resistance. If you're on a very soft rock, then you have low lithological resistance. So where would you expect lots of erosion to be happening, and where would you expect less erosion to be happening? Well, if you have soft rock, you'd expect more erosion. So the left-hand side of that graph, on low lithologic resistance, yeah, you've got high erosion rates. As you increase your lithological resistance, well then, yeah, understandably you're getting lower and lower erosion rates because you're getting harder and harder rock, so it isn't going to erode so well. Okay, so far so good. Now, just before I move on to the next slide, just think, what's the correlation, if I was to draw a graph now, between lithological resistance and gradient? So if I have hard rocks, am I going to get steeper slopes forming on them or gentler slopes forming on them? If I have soft rocks that can't really support their own weight because they're so weak, then on those soft rocks, am I going to get steeper slopes or am I going to end up with shallower slopes? Maybe just think about that for a second. If you want to pause the video and have a think about that so I don't spoil the surprise for you, think it through, and then I'm going to move on. And, well, here's my argument. The argument is, at the top of the diagram here, that if you increase the lithological resistance, in other words you get harder and harder rocks, you can support steeper and steeper slopes. So you don't get tall vertical cliffs in soft mud, but you do get tall vertical cliffs in granite. So as you increase the rock resistance, the hardness of the rock, for want of a better simplification, as you increase the resistance, you'll get steeper and steeper slopes. Well, if you combine that graph, the fact that as you get steeper slopes, as you get more resistance, you get steeper slopes, what that means is that you actually get the same amount of erosion regardless of what gradient you're on or what your lithological resistance is, because those two are inversely related. So in the bottom left-hand side, as you increase the slope, as we move along the bottom of the graph, why aren't we increasing the erosion rate as you'd expect to as we're increasing the slope? Well, it's because in the background, we're also, as we increase the slope, we're probably dealing with slopes made of harder and harder rock, and that's how come the slopes can be steeper. And on the right-hand side, as we increase the lithological resistance, well, why aren't we as we increase the resistance, why aren't we therefore decreasing the erosion rate? Well, it's again because we have this hidden correlation, if you like, that's in the top graph there between slope and lithological resistance. So according to that kind of logic, the landscape doesn't necessarily flatten out through time as erosion proceeds, because there's a balance. I hesitate to use the word, but I'm going to. There's an equilibrium between what's happening in terms of gradient, what's happening in terms of rock resistance, and what's happening in terms of erosion rate. And if you meddle with something, there are feedbacks and there are compensation factors. You're trying to make the slope very steep. Well, if you're doing that on a soft rock, well, it won't stand for it. You're trying to do lots of erosion on your steep slope. Well, if it's on a hard rock, it's not going to stand for that. So there are all these interacting complex factors at play, according to Hack's model. So over the course of time, as we're watching a landscape develop, there are lots of different things going on and lots of different ways of thinking about those things, lots of different hypotheses or ideas as to how the landscape is working. So who was right, Davis or Hack? Well, based on what I said before about the landscape being complicated, you can imagine I'm probably not going to say that one is right and one is wrong. Like I said previously, if you look at something over different time scales or different spatial scales, whether it's the life in general or aspects of physical geography, you get different answers as to how things are working depending on the scale that you look at. That was the whole point at the beginning of this session. So whether you want to say, yeah, Davis is right, or oh no, Hack was right, well, it depends again on the scale at which you look, partly on the time scale at which you look. And we've talked about these graphs previously, but Schumann-Lichty in 1965 talked about different scales of time in geomorphology or in physical geography, and they referred to the longest period of time as being cyclic time. And on that left-hand graph there, over cyclic time, gradient gradually decreases over the course of time. You can see the landscape changing on that cyclic time scale, and it's changing in a very clear direction, a bit like Davis said, over cyclic time, yeah, there's a gradual decrease in the gradient over the course of time. But let's zoom in a little bit, and on that left-hand graph I've just flagged up, well, they've just flagged up there a little point on that curve, and they call it graded time. And let's move over to the right-hand graph now and look at graded time more closely. And over the course of graded time, which is some much shorter time period, so imagine now you're thinking about rivers eroding a landscape, and instead of looking over millions of years like we were on the left-hand graph, we're now going to look over maybe hundreds of years, tens or hundreds of years. And on that shorter time scale, we're seeing changes. Things are going up and down, the valley's getting a bit wider, a little bit narrower, the stream's getting a little bit steeper, a little bit less steep, you're getting some erosion, you're getting some deposition, a storm comes through and something else happens. So things are happening, but it's not clear on that right-hand graph that we're steadily losing, decreasing in gradient over the course of time. It's going up a bit, down a bit, up a bit again. And so you're not seeing the same thing at that time scale, graded time, as you were seeing over the much longer cyclic time scale. And in that right-hand graph, they've also just marked on an even shorter time scale, which they've called steady time. And steady time is a time scale over which you can't actually really see anything happening at all. So if you're interested in long-term evolution of the landscape in response to fluvial erosion, and you walk down and have a look at the River Trent for 5 minutes this afternoon, in that 5-minute period of watching the river, you're probably not going to see anything happening that has any relevance really to the long-term evolution of what's going on. You're not going to see the river system changing significantly in 5 minutes. That kind of thing happens over much longer time scales. So what you see depends partly on how long you look for. A bit like measuring the coastline of Britain. What you measure is going to depend on how closely you look, how closely you measure it. So how landscape changes over the course of time depends on the time scale that you're choosing to look at it over. And if you look at something over a short enough time scale, you won't see any change at all. And that brings us to this question of equilibrium. Can things, like Hack was saying, can things be in balance so that some aspect of the landscape doesn't actually change because other things are working around and keeping themselves in check, keeping each other in check to maintain that balance or equilibrium? That's a really important question, and that's what we're going to come on and talk about next. But I think I'll give you a break and we'll come back to that in a follow-up video in the second part of this unit's videos.